Good morning, everyone. In this morning's class, what we're going to do is we're going to review problem formulation. First, we're going to look at the homework problems from last time, and then we're going to continue on. The reason I've gone to recorded video format is because a lot of this is new. A lot of it helps with repetition. If you see it just once during class, it may be hard to recall a week later or even 2 days later. So what I'm going to do is I'm going to prepare these videos. They'll be uploaded to my YouTube channel. And if you have problems with this, you're able to go back into it and watch it on your own at a later date. So let's begin. When we're formulating linear programming problems, now, complex or simple, there are typically 4 steps that we want to follow. The first step, very simply, is finding the decision variables. What I mean by that is we want to find what is being decided upon. If we have a company that makes TVs and stereos, what we're looking for is deciding how many TVs, how many stereos. Those become our decision variables. If we're in a situation where we're deciding upon maybe a menu, what to eat on a given day. Maybe we're deciding between hamburgers and chicken. That too is a decision variable. That's also something that we're deciding upon. So for each of them, whenever we look at the problem, the first step is deciding what are we deciding in this question. Whatever we are deciding, that becomes x1, x2, x3, etc. We don't always have one thing that we're deciding. Sometimes we have many, sometimes we don't. It always depends, but however many things we are deciding upon, those become our decision variables. Okay, so in this scenario, or once we've found our decision variables, then we have to create our objective function. And that is, how do our decision variables relate to real life? For example, if we generate X amount of money for item A, X1, and X amount of money for item B, X2, that is how our decision variables relate to the values given in the question. Maybe we're trying to minimize our money spent on food items. If a pizza is $6 and a hamburger is $4, we have to be able to relate those problems. And that's where our objective function comes in. Once we've found what we're deciding and we know how what we are deciding relates to our system, that's when we're able to, that's when we're able to find our constraints. We always have limitations governing the choices we make. Those limitations, another word is constraints. For example, if I want to build a TV, but I only have 30 hours of labor available, I cannot build an infinite number of TVs. It doesn't work that way because of the limitations placed on me. So in that scenario, we have to look at it like this. We have to look at it as those limitations governing our choices. Okay? Finally, once we've done all 3 of those, we have to collect everything together. And by collect everything together, these questions are always given in the exact same format. It makes it easy to read, and if we solve the problems, it makes it much more clear when we're solving problems manually or plugging information into our system, our computer programs that will help us find the problems. So let's begin. I'm going to go through these problems that we did last time, and then we're going to move on to some more, and hopefully through repetition with my instruction, this becomes clear to you on how to formulate linear programming problems correctly so that they can be easily solved in the future. So, without further ado, let's begin. A junior student earns $20,000 during her summer internship. Since she plans to pursue her graduate studies, she wants to invest all her earnings in an annual tax saver scheme and a non-tax saver plan. The tax saver plan yields a return of 8% with a risk score of 3. The non-tax saver plan yields 10% with a risk score of 5. To use the tax exemption, the student has to invest at least 50% of her investment in a tax saver scheme. A finance professor advises the student to keep the average risk score of her investments to no higher than 3.6. Formulate a linear programming model to maximize the return on investment of the junior's earnings. So we're gonna alter our question here, just so that we're able to see effectively what changes, what highlighted information is key. So looking at this question, we're going to see our first step. So we'll go right here, we'll start a new slide. We'll call it problem formulation 1. And what we have to do is we have to decide, the first thing we have to decide is what is being decided between. So we know the student. Let's highlight our key information. So maybe 20,000 is important. We're not sure yet. She wants to invest all her earnings in an annual tax saver scheme and a non-tax saver plan. Well, right here, we probably know we've found our decision variables, but let's continue reading for right now. The tax saver plan yields a return, so tax saver is 8%. It has a risk score of 3. The non-tax saver yields 10% with a risk score of 5. So we have a lot of key information here. I'm just going to correct a couple small mistakes I've made. To use the tax exemption, the student has to invest at least 50% of her investment in the tax saver scheme. A finance professor advises the student to keep the average risk score of her investments. So average risk score no higher than 3.6. So we've got our key information here. We know now we're deciding between two different things. We're not deciding on risk. That's not our key decision. We're not even deciding on return. That's not our key decision. Instead, we're deciding between annual tax saver and non-tax saver. So tax saver equal to X1. Non-tax saver equal to X2. So now we have our decision variables. Looking at this problem, it doesn't directly say what she plans to pursue her graduate studies. It doesn't exactly say what she's trying to do, but I think from the question, and sometimes this is the case, from the question we know she wants to maximize her return, right? We see that here. Because it's money, it's an investment, nobody likes to lose money when they invest. So we're going to assume, and we're correct in assuming that we're going to maximize her investment. So we come back here, we go to max Z, always max or min Z. And Z doesn't have to be entered in. but I will enter here its return on investment. And our maximum, our return on investment, we see is X1 is the tax saver plan, 8%. The non-tax saver plan yields 10%. So now we have how our return on investment relates to the real world. So we come back here and we make it 0.08 x1 plus 0.10 x2. That's how we're generating. That's how we're generating our information. That's how we're going to determine our return on investment. So we come back to our question. Now we see there's a couple limitations governing what we're able to do. The first one is risk score. So our risk score for non-tax saver, we have a risk score of 3. That's the tax saver. The non-tax saver is a risk score of 5. Between both of those, we need a risk score of no higher than 3.6. That information, or that tells us how to formulate our first problem constraint. So we come back here, and we say our first constraint, our first limitation is 3x1 plus 5x2 must be less than or equal to 3.6. And that represents our total risk score. We see that here. We have risk score of 3 with tax saver, so 3x1 because tax saver is x1. And we have 5x2 because non-tax saver is x2. And we want it no higher, so less than or equal to 3.6. We're almost finished. The last thing we have to know is the student has to at least invest at least 50% of her investment in a tax saver scheme. Whenever we do things like this, sometimes we have alternate ways to do it. There are a couple different ways we can do this constraint mathematically. But for simplicity's sake, we're going to make it easy. How much does the student have to invest? The student has $20,000 to invest. What is 50% of $20,000? $10,000. They cannot invest less than $10,000 in the tax saver scheme. So we come down here and we make our second constraint, 2. So X1, which is our investment in the tax saver, must be greater than or equal to 10,000. There are different ways we can do it, but all of this works. So we see here, we have our decision variables. We have our objective function, and we have our constraints. The only thing remaining is to put it all together, and that's what we'll do here. So max z is equal to 0.08 x1 plus 0.10 x2 subject to, and this just means under the limitations of, (3x1) plus 5x2 less than or equal to 3.6. Constraint number 2, we have x1 is greater than or equal to $10,000. This is our problem formulation. With this number, we can solve either mathematically or by plugging it into management science software to determine the answer almost instantaneously. Both of the, once we've reached this stage, solving the problem is quite easy. The only problem is formulating the problem, and that's what we've done here. Hopefully there are no questions. We'll move on to the second question momentarily. Okay, everyone, welcome back. In this second example, we're going to continue on. Oh, sorry, I skipped to the wrong one. In this second example, we're going to carry on. Here, once again, we're going to begin by looking at key information. So let's go through the example now. A carpenter makes tables and chairs from wood and fiber. The store has 50 units of wood and 4 units of fiber. Each table requires 20 units of wood and 40 units of fiber. Each chair requires 6 units of fiber and 4 units of wood. So we have both what we're making and what's required to make them. The store has to use a minimum of 20 units of fiber. The demand for tables is no more than 2. Each table is sold along with at least 2 chairs. A table and a chair earn $300 and $200 in profit respectively. Formulate a linear programming model for the problem with an appropriate objective function. So as always, the first thing we need to do is find decision variables. But before that, let's highlight the key information. A carpenter makes tables and chairs. So already we know probably what our decision variables will be. And they're made from wood and fiber. Typically, if we're looking at resources, those qualify generally as constraints because they are not unlimited. The store has 50 units of wood and 4 units of fiber. Each table requires 20 units of wood and 40 units of fiber. Each chair requires 6 units of fiber and 4 units of wood. What we've just highlighted is A, how much wood and how much fiber are required for each table and chair, as well as the total units of wood and fiber. But there is one mistake. These numbers were incorrect, so it's 40 units of fiber held by the store, and a table requires 4 units of fiber. The store has to use a minimum of 20 units of fiber. That's another constraint because that limits our decisions. Anything less than 20 units of fiber is not a valid response. The demand for tables is no more than 2. Another constraint. Each table is sold along with at least 2 chairs. Again, that's limiting us. We cannot sell an uneven number of, or if we sell a table, we cannot sell only 1 chair. A table and a chair earn $300 and $200 in profit, respectively. So we've highlighted our key information here. The next step is creating a new slide, and we'll call it Problem Formulation 2. And we have to select our decision variables. So in this situation, what are we deciding? We're deciding how many tables and how many chairs to make. Those become our decision variables. X1 equals tables, x2 equals chairs. Now we have to relate that information back to the real world. So a table and a chair earn $300 and $200 in profit respectively. It doesn't say here what we're trying to maximize, but because it's a manufacturing problem, and because this carpenter probably wants to make money, we're going to assume he's trying to maximize profit. So we can do our objective function here. Max Z, and that represents profit in this situation, is equal to 300 x1. And we see that here, $300 for every table, $200 for every chair. So 300 x1 plus 200 x2. And that represents for every table we make, we get $300. For every chair we make, we get $200. We're attempting to maximize how much money we make. Looking at the problem now, it's very clear we should make more tables. They're more money. However, we don't yet know how many resources go into each and what other constraints might limit our decisions. So that's what we have to do now. We have to list our constraints. So C1 I'm just doing this for ease of reading later. C1, in this situation, let's look. The store has 50 units of wood and 40 units of fiber. So automatically we know these are limitations. Anything that requires more than 50 units of wood doesn't work. We only have 50, we cannot get more. So our first constraint is available wood. So C1, we'll say 50 units Now, let's go back to our question. And we see each table is 20 units of wood. And each chair is 4 units of wood. And I paused my recording because, again, I think I made a mistake, and I did. It's only 10 units of wood. That doesn't affect anything yet. So each table requires 10 units of wood. Let's highlight that one. And each chair is 4 units of wood. So tables are x1. So 10x1, which is the wood for each table, plus 4 units of wood for a chair, so 4x2 must be less than or equal to 50. And what that says is every table we make requires 10 wood. Every chair requires 4 wood. We have only 50 units of wood available. So anything more than that is impossible. That's what we've indicated here. This limits our decision-making power. So then we do C2, and we know that's fiber. We know that we have 40 units of fiber. So let's go back into our question, and we see that a table is 4 units of fiber, a chair is 6 units of fiber. So we come back here, and we go 4x1, which is 4 units of fiber per table, plus 6x2, which is, again, 6 units of fiber per chair, and it has to be less than or equal to 40 units of fiber. So what we're able to see is our first 2 constraints are right here. how much wood and how much fiber for each table of chairs. We also know that fiber must be a minimum of 20 units. So we know here our fiber equation is already given to us. So C3, our third limitation, we know is 4x1 plus 6x2 because that's how much fiber we're using. Must be greater than or equal to 20. And what that means is fiber must be more than 20 units used. Between tables and chairs, we have to use more than 20 units, but we cannot use more than 40. So what this is telling us is our fiber usage has to be between 20 and 40 units. That's what we're seeing here. C4, we have a fourth constraint. This problem is a little bit more complex. So the demand for tables is no more than 2. We've done this constraint. Our next constraint is the demand for tables is no more than 2. So we come down here and we go, tables is represented by x1. So x1, number of tables, must be less than or equal to 2. If x1 is equal to 3, that is not a valid equation because we only have 2 demanded. That's what we're seeing here. Okay, x1 is less than or equal to 2, which is the maximum demand for tables. We have one more constraint, again, more complex than the last problem. So let's go back. Each table is sold along with at least 2 chairs. So for every table we sell, x1 is tables, must be equal to a minimum of 2 chairs. So it must be greater than or equal to 2, x2. For every x1, if x1 is 1, x2 must be 2. It can be more than 2, but it has to be a minimum of 2. Tables sold with chairs. Now the way the equation is formatted here would not work in a computer program, but for now that's not something we have to worry about. So let's do a new slide. Because we want to collect all of our information in the appropriate place. So we say max z equal to 300 x1 plus 200 x2. Subject to C1, C2, C3, C4, and C5. C1, we'll go back, we'll see 10x1 plus 4x2 is less than or equal to 50. 10x1 plus 4x2 less than or equal to 50. C2, and we'll continue the pattern. 4x1 plus 6x2 is less than or equal to 40. We don't need all of the titles that we put in here. This is just for our comprehension. So when we're doing our problem formulation, these aren't necessarily useful, so we can omit them. Here's our minimum fiber use for x1 plus 6x2 is less than or equal to 20, greater than or equal to 20. We have our fourth constraint. Demand for tables, x1 is less than or equal to 2. And finally, our fifth constraint, x1 tables must be greater than or equal to 2x2. So what we've done is we've completed the problem formulation in the correct format. This is the acceptable answer. Hopefully there are no questions. Let's move on to our third example now. Begin by reviewing the question. The Pinewood Furniture Company. And the reason this is so similar is I want you to see, even with similar problems, the constraints and everything else can change significantly. So this is very similar to the last question, but a lot of the numbers and even the constraints will be different because we have different limitations in this situation. The Pinewood Furniture Company produces chairs and tables from two resources, labor and wood. The company has 80 hours of labor and 36 board feet of wood available each day. Demand for chairs is limited to 6 per day. Each chair requires 8 hours of labor and 2 board feet of wood, whereas each table requires 10 hours of labor and 6 board feet of wood. The profit received from each chair is $400 and from each table $100. The company wants to determine the number of chairs and tables to produce each day in order to maximize profit. So again, let's highlight our key information. Pinewood Furniture Company produces chairs and tables from two resources, labor and wood. So automatically we kind of assume that we're going to have these two things as constraints. The company has 80 hours of labor and 36 board feet of wood available each day. So now we know our maximum labor every day and our maximum amount of wood every day. Demand for chairs is limited to 6 per day. Each chair requires 8 hours of labor and 2 board feet of wood. Each table requires 10 hours of labor and 6 board feet of wood. The profit received from each chair is $400, from each table $100. We've highlighted all of our key information here. Now, as before, we'll come in, we'll do a new slide, problem formulation 3. And we'll begin highlighting our key information. So we see here, the Pinewood Furniture Company produces chairs and tables from two resources, labor and wood. The company has 80 hours of labor and 36 board feet of wood. These are resources. So let's stop here at the very beginning and we look at produces 2 items, chairs and tables. Those are going to be our decision variables. How many chairs do we produce? How many tables do we produce? So x1 equals chairs, x2 equals tables. That's what we've done so far. Now, next thing we have to do is our objective function. We see here the company wants to determine the number of chairs and tables to produce each day in order to maximize profit. So we see right away, this is a maximization problem focused on maximizing profit. So max Z is equal to profit. Profit is equal to, nope, we see $400 from a chair, $100 from a table. 400 x1 plus 100 x2. That's what we found so far. Now, as before, we're going to focus on constraints at this point. We have two constraints that we have to look at. We have several constraints to look at. The first is that the company has 80 hours of labor available. That's going to be our first constraint. C1 is 80 hours of labor available. Then we go back and we check. Each chair, so X1 is 8 hours of labor. Each table, X2, is 10 hours of labor. Now we have our first constraint. So 8 X1 plus 10 X2 must be less than or equal to the 80 hours of labor we have available. To make a chair is 8 hours. To make a table is 10 hours. But we have less than or equal to 80 hours because that's our total amount of labor available. We also have our second constraint, which is very similar. We see here that we have 36 board feet of wood available each day. So, one more time. And again, these labels aren't necessary, but they do help with comprehension. So now we know how much is available, and we have to check how much is required. So we see here, each chair requires 2 board feet of wood. Each table is 6 board feet of wood. So we have 2x1 plus 6x2 is less than or equal to the 36 board feet we have available. This is our second constraint. Now we could have, if we see here, demand for chairs is limited to 6 per day. It does not matter in the order that you write the constraints, as long as all the possible constraints are included. So let's go back and we see the demand for chairs is limited to 6 per day. Chairs is X1, so C3 X1 is less than or equal to 6. And that's our maximum demand for chairs. So we've accounted for labor and wood, demand for chairs, demand for everything. Our problem has been solved. This time we had only 3 constraints. So we collect everything as before. excuse me. Less than or equal to 6. So this becomes our complete problem formulation. With mathematics or using linear programming, managerial science focused computer programs, we would be able to solve this very easily now that it's been put into question format. Okay, so these are the 3 questions we reviewed last class. Hopefully there are no problems, and we'll continue shortly. Okay, your only homework problem today, or in this first section, is this next problem. We've already covered 40 minutes, so it's a very short, simple problem. I'm going to upload this information to our group chat when I upload the videos later. I would like you to solve this problem. You own a pizza restaurant and you have just received an order for 100 pizzas for tomorrow. However, tomorrow is a holiday, so you are currently out of supplies. You also don't plan to open after preparing the big order, but you do need enough supplies to make the big order. To make 100 pizzas, you require 15 kilograms of pepperoni and 20 kilograms of cheese. You also have 2 ways of acquiring supplies. You can buy a large ingredient bag that contains 3 kilograms of pepperoni and 1 kilogram of cheese, or a small ingredient bag that contains 1 kilogram of pepperoni and 2 kilograms of cheese. The large bag is $5 and the small bag is $4. So you do not have to upload this problem anywhere, but we will discuss it next class. This is your homework assignment for the first section that we've just completed. Thank you everyone for listening, and I will see you in our next section.